Yeah. Yeah. Well, the assignments are going to be straightforward, but I'm planning to cover more material than I typically cover because you guys are so smart. We have about half of the semester left, and we are almost at the spur gear design. So I'm planning I will probably wrap up the gear design and start with internal combustion engine in next few weeks. So in today's class, I'm gonna work out the problem. I trust that you haven't forgotten the gear design procedure. So I'll just jump onto the problem. So design a spur gear pair. So this means gear and pinion. The center distance is equal to 500 millimeters. Input RPM is equal to 900. Output RPM is equal to 200. Torque to be transmitted is equal to 5000 Newton meter, and starting torque (25% more). Now, one thing we have to understand that typically when you start, there is friction, there are inertia effects. So the starting torque that is always more. So we want our gear design to be safe not only for continuous torque transmission, but also for the starting torque transmission. Now here are some guidelines that are already provided. Is find module and width. Module and width for 20-degree stub. Second, find number of teeth. Then find pitch circle diameter, and then design shaft. So I'm going to take a shortcut. I'm going to assume that gear and pinion are made up with same material. Now what happens when I make that assumption? It saves one step, which means when the gear and pinion that are made up with same material, pinion is weaker. So what we are going to do is we are going to design pinion. In the event that the gear and pinion are made up with different material, then the right thing to do is to basically check which one is weaker, whether the gear is weaker or the pinion is weaker. Now, just to give you an understanding of what the application is, we have an electric motor. This electric motor is running at high RPM, low torque. So basically you have T1 omega 1, where speed is high, torque is low. Now what we are going to do is we have the inputs RPM. So clearly what this means is pinion, it attached to the input shaft, and the gear is attached to the output shaft. And this is the input, this is the output. Here, this is T2 omega 2. Please note, power is constant, which means T1 omega 1 is equal to T2 omega 2. So we can manipulate the speed, and accordingly, the torque will change. Now, one thing that I want to go about is they have given sort of a constraint, a geometric constraint on the center distance. What does that mean? It means that the center distance of the shafts is 500 millimeter. And if you think about it, this is the gear, this is the pinion. So indirectly, they have given us the information about the geometry. So if this is the gear diameter, I'm going to call dg divided by 2. If this is dp divided by 2, center distance naturally has to be dg divided by 2 plus dp divided by 2. Are you with me so far? The radius of the big gear and the radius of the small gear, which is pinion, should be equal to the center distance. And one of the important part of the gearing is module for the small gear and module for the big gear. They must be one and the same. So for design, module must be same. You cannot mesh 5 millimeter module pinion with 10 millimeter module gear. Module must be same. I also know the relationship between module and the diameter. So D is equal to M multiplied by number of teeth. So what this means is DG is equal to M multiplied by TG, where TG is the number of teeth on the gear. So now, if you look at one more expression, is the input RPM is 900 RPM, output RPM is 200 RPM. So that clearly tells me the ratio between the two, the gears, the gear and pinion is 900 divided by 2. So the reduction ratio RR is 900 divided by 200, which is equal to 4.5. What that means is the big gear DG is 4.5 times diameter of the pinion. In other words, number of teeth on big gear are 4.5 times the number of teeth on small gear. I would repeat this argument once again. So reduction ratio is 4.5, which means the diameter of the gear divided by diameter of the pinion is equal to 4.5. So what I can do is I can actually use this relationship. I can use this relationship to find out the values of dg and value of dp. So in other words, dp is equal to 4.5, dg is equal to 4 times dp. So the center distance is 500 multiplied by 2 is equal to dg is 4.5 dp plus dp, and that yields dp is equal to 182 millimeters and dg is equal to 820 millimeters. Now, the next step that what we want to do is we want to find out something called as the pitch line velocity. What is this pitch line velocity? Can someone tell me the law of gearing? Law of gearing. For a smooth, continuous power transmission, point of contact must lie on the line of centers. POC should lie on LOC. So the velocity P, VP, whether you consider that either on the gear or on the pinion, it would be one and the same. So VP is equal to pi times diameter of gear multiplied by the speed of gear divided by 60, or pi times diameter of pinion, speed of pinion divided by 60. So I can use any equation. We already know the value of diameter of the gear, which is, or we can use diameter of the pinion, it doesn't matter. Pi times diameter of the pinion is 182. Speed of pinion is 900 divided by 60. That gives me the velocity, and I'm going to write this in meters per second, which is 8.6 meters per second. Now, why do we need to find this velocity? Because please understand, the loading on the gear is not static. But our analysis, the back of the envelope calculations that we did, they assumed static loading. So to account for the errors and to relax the assumptions, we used something called as the velocity factor. Velocity, or the pitch line velocity, is needed to find velocity factor. To find velocity factor. So 8.6 at this point, if you have the textbook, I would strongly recommend that open the electronic copy of your textbook or the hard copy of your textbook and tell me what velocity factor would you use. And the reason I want to do this exercise, that way you know where to look for the values. You are going to do the exact same thing for the helical gear. You are going to do the exact same thing for the bevel gear. You are going to do the exact same thing for worm and worm wheel. So can someone quickly tell me what is the velocity factor? Just do this exercise. That way you won't struggle when you have to find these values all by yourself. Correct. So please note, and can you tell me the page number or the table number? 1039. Okay, so since V is less than 12, 1039 page. So go to page 1039, and that is where you will see the velocity is less than 12.5. That's why your CV, which is the velocity factor, is 3 divided by 3 plus V, which is 3 divided by 3 plus 8.6, and the answer that I got is 0.26. Are you with me so far? Now, please note that I made my life easier by assuming gear and pinion are made up with same material. So that's why I'm skipping one step. I know the pinion is weaker, so I'm going to design the pinion. And that came about because I assumed the gear and the pinion are made up with the same material. Now, what material do you want to choose? The classic material for usual gear application is steel. And now what I want you to do is, I want you to quickly look at the table and the material and tell me the value of sigma O, which is for steel. Okay, let's go with 140. Well, your material, not mine. Sorry.
Do people ever use untreated cast steel, or would you always treat?
If you start treating steel, it increases the cost. So for most general purpose application, 140 Newton per millimeter square is good. Just to give you a sort of the normal steel that we use, actually that can go, the failure that can go up to 380. So steel is very, very strong. By heat treating, you make it stronger. So unless, but then the cost of the steel, cost of the gear, cost of cutting the gear all increases. So unless it is specifically specified, you just stick to a simple steel configuration, steel gear, steel pinion. So 140 is a good number. Can you tell me the table number or page number where you got this number? Okay. Oh, wow, you remember the table number. That's nice. Okay, so next part is I want to find out number of teeth on pinion. There is a long route and a short route. So now I want you to tell me what are the minimum number of teeth that I need for this pinion. So tell me number of teeth. Why 18? Oh, so and I want you to just look at the design data book. There is minimum number of teeth to avoid interference, and there is a mathematical expression for that, but I don't use that mathematical expression. I just use the table. So minimum number of teeth, what type of teeth geometry are we using? 20 degrees stub. You agree with me? 20 degrees stub. So minimum number of teeth that I want to use is 18. Everyone okay with that? If you say 20, I'm not gonna complain. Yeah, 14 is okay. You can actually go with 14 as long as you have the data sheet that is supporting 14. So number of teeth is equal to 18. Okay, then what we want to do is we want to find out Lewis's form factor. Now for Lewis's form factor, tell me the equation. And I'm trying to go through this exercise step by step, because when you work out the gear problem, initially you may struggle which table to use, where to go, what values to pick. 175 minus 0.841 divided by. Correct. And our number of teeth are 18. Very good. So you get value of y. Are you with me so far? Yeah. For 20 degree stub? I don't think so. So basic. That's for 20%. Which? So what is the page number? Can you tell me? Page number?
Oh, sorry, 1038.
1038. So, and but as Mason just said, that minimum number of teeth to avoid interference is 14. So if you want to choose 14, I'm totally okay with it. So if somebody says, no, I want to go with 14, that's totally fine. So you can use 14. Next step is the fundamental equation. Force is equal to stress multiplied by area. And that equation comes about something like this. I will write the equation. Force is tangential force multiplied by, you're going to have sigma, which is sigma W, multiplied by B, multiplied by pi, multiplied by M, multiplied by Y. WT is equal to tangential force and since here is something that you want to be super duper careful about. So the torque to be transmitted is 5,000 Newton meter. So the torque, now unfortunately it is not clear at this point whether this torque is transmitted by the gear or the torque is to be transmitted by the pinion. So just to be on the safer side, I'm going to assume tangential force is equal to torque transmitted by pinion divided by the radius of the pinion. Now this is an important observation here, because if you assume that the torque that is given is the torque transmitted by the gear, then you will have to use the radius of the gear. Everyone with me so far? Not the pinion. So torque is 5,000 divided by the diameter of the pinion is 182 dollars to dollars, pesos to pesos. So you need to have 5,000 divided by 0.182, and that gives me the equation for the torque, tangential force. I didn't really work out this problem. So can someone tell me what is this value here real quick? Sigma W is equal to sigma O multiplied by the velocity factor. Sigma O is 140. The velocity factor 0.26. So what I would do is I would substitute these values. Now B is the face width divided by module. I will assume this ratio to be 10. Times M multiplied by pi multiplied by M multiplied by Y, and tell me value of Y. Can someone tell me value of Y? Value of Y comes from here. Y is equal to 1.75, 0.841 divided by 18. But one thing, don't forget, this tangential force is calculated based on the continuous torque. But at startup, the torque is 25% more. So whatever WT we get from here Can someone tell me what is the value of WT here real quick? 54.9 kilonewton. Okay, so I need to multiply this by 1.25 multiplied by 54.9 10 to the power 3. And this equation, the only unknown is m. So please solve and tell me what is the value of m. What is the value for m? 2.7 millimeter.
2.795.
Can someone check real quick? Two 2.75 millimeter, 4 millimeter, 5 millimeter, 10 millimeter, 15 millimeter.
Okay.
60 millimeter. 19.37. Everyone is getting different answer. Well, it's a design class. That does not mean you should calculate wrong answers. Just make sure there is m square. So make sure that sigma 10 times m pi m multiplied by y, it's giving you some meaningful numbers. And unfortunately, no two numbers are matching. So I can't really go with 3, or I can't go with 20, or I can't go with 6. Anyone else? Oh, 60. Somebody got 60. 60 millimeter module, man. That's going to be a big gear.
I got the different, when you find the tangential force, are you supposed to use the starting torque or the running torque?
So basically so we have to take the continuous torque, multiply that 1.25 times, and then finally get the value of m. No, so look at the expression. So basically this becomes m, there is m here and there is m here. So there is a square root operation that you guys have to do somewhere. Okay. So module of 21.63. So module of 22 millimeter. Now, here is a problem. Now, the problem here is, think about what we have. We have identified the number of teeth. Number of teeth is equal to 18, right? We have already identified so we found out module 22. So if we were to use these many number of teeth and this module, what's going to happen? We are going to get the diameter of the pinion which will be 18 multiplied by 22. And we know that based on our kinematic calculation, or based on the geometry, our diameter of the pinion has to be 182 millimeter. So this is what we need from geometry. And I'm assuming your calculations are correct, but this is what we are getting from calculations. So something doesn't make sense. The question here is, now what? How do I address this issue by least amount of rework? How do I address this issue with the least amount of rework? This is a very practical design problem. Don't get me wrong. You use equations, you find out and find. Yeah, go ahead.
Why are you saying it doesn't make sense?
Because 18 multiplied by 22, what do you get? So if you were to choose 22, that is the module that you got from this calculation, you can't change number of teeth. Do you agree with me? So which means you get 396. But we know the center distance has to be 500. That means based on the center distance calculation, we already found out in the previous step, diameter of the pinion is 182. So how do I solve this conundrum with the least amount of effort on my side? You can. But if you change module, then you have to change number of teeth. You can change the width of it. So, but then you can't make it too big or too small. It needs to be within the specifications, like B by M should be between 8 to 12. Changing material. All these are very, very valid options. And if you don't have experience in working out or reiterating the design process for the gear, you can try any of these. That's totally fine. And I'm pretty sure that after 1 or 2 iterations, you will get a combination, certain combination of module, certain combination of face width, certain combination of material that would fit this design requirements. Now, how would I go about it? So for that, I'm going to take you back a minute and I'm going to go the very first calculation that we did. Center distance is given to us. Center distance is given to us. Reduction ratio is given to us. That means you agree with me. Reduction ratio is given. Center distance is given. We do not have any control over the diameter. So diameter has to be the same. So diameter, no matter what you do, diameter has to be 182 and 820. Do you agree with me? Now, let's go to the next equation for VP. Since diameter is fixed, we know the pitch line velocity, which means the velocity factor CV is also fixed for us. You agree with me? What is not fixed that we chose is number of teeth. So the minimum number of teeth are 14. What happens if number of teeth increase? If you increase number of teeth, then clearly here is what's going to happen. Your diameter of the pinion, you don't have any control with. So you don't have any control over the diameter of pinion. If you increase the number of teeth, your module has to go down. Are you with me so far? So you can change number of teeth. You can increase number of teeth, and that would be okay. But another way of attacking the same problem is playing with the material. So clearly at this point, the design does not fit design constraints or geometric constraints. So I'm going to show you a simple way I would address this. What I would do is I would change the material. Now, if you change the material, the question is, what should I use? And what strength I should use? So I'm going to cast this problem slightly differently. So what I would say is, do something like this. Diameter of the pinion is 182 millimeters. Number of teeth, which is TP, we chose to be 18. What is the module based on this relationship? What is the module based on this relationship? And clearly, the module is 182 divided by 18. Do you agree with me? And that answer is it would be a little bit less than 10, but I would say 10, approximately 10 millimeter. Now I would start with this module, and what I would do is I have two choices. This is super important. So look at the equation for WT. WT is equal to sigma W multiplied by B multiplied by pi multiplied by M multiplied by the Lewis's factor, which we already found out, which is Y. So here is what I'm going to do. I will show you both ways. First, I'm going to start with the material. So I'll say 1.25 multiplied by 54.9 10 to the power 3. Sigma W is velocity factor multiplied by sigma O multiplied by B multiplied by pi multiplied by M multiplied by Y. Velocity factor is not going to change. Velocity factor is 0.26. So this is option 1. Okay. Option 1. 0.26. Sigma O. B is 10 times M, and we already found out what is the value of M. So this is M. 10 times M multiplied by pi multiplied by 10 multiplied by Y, and we know the value of Y, which is 0.128. And please quickly tell me what is the value of sigma O. No. So look at the equation that I have written. Can you see there is only one unknown for equation sigma O? So use your calculators and tell me the value of sigma O. And tell me, does a material exist with that value of sigma O? No pain, no gain. Okay, that is the design. Back and forth, back and forth. That's why the exams and homeworks are take home.
Sigma O is 656.7.
Sigma O is 656 Newton per millimeter square. And I'm assuming the calculations are correct. Go back to design data book and tell me, is there a grade of steel that can support sigma O at 650 or say 700 Newton per millimeter square? Look carefully. Hmm? $196. We have a problem. Houston, we have a problem. Okay, let's go with option 2. Option 2 is option 2. So I'm going to keep the maximum value. I know that something is goofy here. So I'm going to say my sigma O is 196 Newton per millimeter square.
Oh, sorry, you said any steel?
Of course, any steel.
So there's an alloy steel that's the highest of 472.
Okay, so there is alloy steel, which is 472. So anyway, we are not making the gear. Might as well, even if you say gold, that's totally fine. It's not a wise engineering choice, but for the purposes of design, that's okay. So you can say alloy steel, and alloy steel value of sigma O is 472, 470 Newton per millimeter square. So what I'm going to do now is I'm going to repeat the same calculation. 1.25, 54, 10 to the power 3 is equal to, remember the same equation, we have CV sigma O B multiplied by M multiplied by Y. CV value is 0.26. Sigma O value 470. Now what I'm going to do here is I'm going to say B is unknown and M is 10 multiplied by Y, which is 0.128. And tell me what is the value of B. Oh, did I miss pi? Yes. Oh, yeah, yesterday was pi day, right? No, day before yesterday was pi day. So. Okay, tell me, what answer do you get? There is one more pi in the equation. Did I miss 2 pi's? One more pi in the equation. Oh, comment was before you added one. Okay, sorry. 139.65. Okay. Millimeters. So now tell me what is the ratio of B by M. B is 139.6 divided by 10, which is about 14. So I can live with that.
We made our initial assumption that B was 10. Where was that coming from?
Somewhere we had to start. So basically, I mean, clearly that assumption was not the best possible assumption. So I made a mistake. But the good news is, at this point, we can actually correct our mistake and say our B by M will be 14. And that's okay. But if you don't like this, and there is one more trick that you can play with. Is you can simultaneously change multiple parameters, and that you will be able to achieve. But my suggestion to at least since this is the very first problem that we are attempting, let's play with 2 parameters, and then when we have the similar situation after we work out 3 or 4 more problems, we will have a better feel for what parameters to tune or what parameters to change. So, well, design is a process. So clearly, if you land up with the correct answer at the first time, which usually doesn't happen with me, then I would really like to see the iterative process. And I would actually sort of tell you things from my experience. Whatever we are studying in this class, if you decide to pursue career in hardcore mechanical engineering, and all of you are mechanical engineers, you will need this information. So just don't get rid of notes or the books, because I promise you, I still have the notes when I took this class first time. And again, I use those when I went to industry, I use those when I actually do some designs before jumping on to CAD software and doing finite element analysis. So all this information, these tidbits of pieces, tidbits of like experience and all the stuff, that will be super duper helpful when you actually work out a design. So I would really like you to document the iterative process, and so that you can go back to those notes and refer those notes when you go to industry. But if you think you don't want to do that, that is totally fine. I had a student at one point that who actually coded all these equations in Excel. So you just enter the number and it will actually just give you all the values, and he turned in an Excel sheet, and that's totally fine. And I know for the fact that he's using those macros and that Excel sheet as he's working at Honeywell. So whatever you think is appropriate is fine. So I would like to see iterations, but if you land up, hey, if you get right at the first time, I'm totally okay with it. Okay, so as far as this problem is concerned, we found the module, we found the width, we found the number of teeth, we found the pitch, circle, diameter. Yeah.
Since you started off this problem on the module, is it okay if we go straight to like using that equation, solving for sigma O, and since you already know the module, instead of solving the module?
Right, but that may not be, sometimes that may not be the best possible approach. In this problem, that approach will work because the gear geometry is constrained by the dimensions.
Yeah.
But
If it wasn't constrained, you would need to solve for that.
yes, so but many a times you will have more flexibility. And I'll work out one more problem wherein I would stick to the basic gear design procedure. And please understand, this is not the complete gear design problem. This is a subset of gear design problem. If I were to do the gear design, remember, there are 2 important steps that are remaining. The next step is finding out the dynamic load. Remember from the Buckingham pi equation, the big expression. And then the third step is finding out the wear load and making sure that the wear load and then static load exceeds the dynamic load. So that is the actual gear design. So this is not the complete gear design. This is just a problem to start. But I'll work out one more problem where we'll do the gear design. Does that make sense? So I am not complete. There are few more steps that are needed, but this problem specifically does not ask for checking for wear or checking for dynamic load. So that's why I'm not doing those steps. But if you have a gear design problem, those steps are absolutely essential. Okay. So next part is shaft design. Now here the question is, which shaft should I design? If I want to take a shortcut, which shaft should I design? Hmm? Why would I do the pinion shaft? Okay. Now, this is an interesting part. Let me ask you this. Torque on the pinion is more or the torque on the gear is more? So question is this. Torque on the pinion, is it more or torque on the gear is more? So the equation, remember equation, you have omega P TP is equal to omega G TG, right? For the pinion, omega is high, which means torque is going to be low. For gear, omega is going to be low, which means the torque is going to be higher. When you actually work out the gear design equation, and this needs a little bit of discussion, if you look at this expression, we use this expression for the weaker element. We do this, we actually use gear, we actually use pinion, and first find out which one is weaker, whether the gear is weaker or the pinion is weaker. And then we use the module for the weaker element. But if you look at the torque, the maximum amount of force, the maximum force will be coming on here, where basically it actually depends upon the radius. So what you'd have to do is whether you consider torque on the pinion or torque on the gear, the force is going to be Wt. That would be the same Tp divided by dp by 2 is equal to Tg divided by dg by 2. So the point what I'm trying to tell you here is the Wt value, the value of Wt would be same whether you consider it on the pinion or whether you consider that on the gear. But let's look at from the forces point of view. And this requires a little bit of discussion. This requires a little bit of discussion. So this is gear. On this gear, I'm going to show you, say this is the tangential force, Wt, that will give rise to a normal force, Wn, and that will give rise to a radial load, which is Wr. Now, if you look at the tangential load is actually bending here. This is the distance. And assuming that this configuration is a cantilever configuration, so there are some variations possible. But so for example, they haven't said that this gear has to be cantilevered or this gear has to be simply supported. For the sake of discussion, at least for this problem, let's assume that this gear is cantilevered. So the point here is you can design the pinion shaft or you can design the gear shaft. The load is going to be the same. So Wt will be the same whether you consider the gear shaft or you can consider the pinion shaft. Now, this distance is not known, but that we can approximate. And how do we approximate this? We know the face width. This face width is about 140 millimeters. So this face width is about 140 millimeters. I need some space for the shaft. I need some space for the bearing, but I don't want it to be too much so that the shaft deflects because of the load. So I'm gonna say 140. So I would just use say 150 millimeters. And this is an assumption, okay? Assumption. And with this, I'm able to find out the moment in the horizontal plane, and I can find out the moment in the vertical plane. So first, I know the value of WT. Now the question is whether you will take WT continuous or whether you take the WT corresponding to starting torque. The maximum amount of load that will be generated is during starting. So I would use 1.25 times 54.54 kilonewton, 54 into the power 3. This is the force. Wn is going to be Wt divided by cosine of pressure angle. So 1.25, 54, 10 to the power 3 divided by cosine of 20, and Wr is the radial force is going to be Wn multiplied by sine phi. Can someone tell me what is the value of Wn and value of Wr? This distance, actually I did not draw a proportional figure. I think I should draw a proportional figure. That way, that will actually make sense. Yeah, and
is 71,000.
71 kilonewton. Yeah, and Wr
WR is 24,000.
24 kilonewton. Okay. Here in this figure, I did not actually do justice because I did not draw the proportional figure. Please note, face width is 140, and I'm assuming the distance to be 150. So let me show you what I mean by that. So this is the shaft. This is the bearing. So this distance is approximately 140, and this distance is 150. So we don't have a long shaft. A shaft is short, and then half of it, the half of the bearing is considered the center line of the bearing. The distance from the center line of the bearing, which is half of the bearing, to the half of the face width is 150. And let's look at the loads. Wt is coming from the page. Wr is something like this. Wt is coming from the page and Wr is coming like this. So now we need to find out the moments in the horizontal plane and the moments in the vertical plane. So moment in the horizontal plane, mh, is going to be Wt multiplied by 150, and moment in the vertical plane is going to be Wr multiplied by 150. And the answer is going to be kilonewton millimeter. Answer is going to be kilonewton millimeter. Now here comes the important part that I was trying to tell you. The resultant moment Mr is square root of Mh square plus Mv square. Why is that? Because these two moments are in two perpendicular planes. These two forces are perpendicular to each other. Now I need to find out the value of equivalent torque. So TEQ. TEQ is the square root of Mr square plus T square. And let's go a step back. Please note that Wt is same on the pinion or on the gear. Do you agree with me? Wt is same on the pinion or on the gear, but the value of torque is different. Are you with me so far? So the value of torque is different. So now since we are designing the pinion shaft, so pinion shaft, I'm going to use T as torque on pinion. And what is the torque on pinion? Torque on pinion is Mr square plus the radius of pinion multiplied by Wt multiplied by 1.25 square. Please note this is super duper important. Everyone understood this? If you are going to design the pinion shaft, don't use torque on the gear, use torque on the pinion. In this particular case, Wt is the same for gear or pinion, but the radius of the pinion and radius of the gear, they are different, which means torque on the gear and torque on the pinion is going to be different. So, I mean, I wish you can tell me quickly numbers and I would actually calculate this. But once you find TEQ, you can find out TEQ tau is equal to pi by 4, pi by 32, d to the power 4 multiplied by d by 2. So in this particular case, tau, you can assume it to be like 45 to 60 Newton per millimeter square. Substitute this value of TEQ, the value of TEQ here, and then find out the value of D. But I'll tell you something funny that is actually I should work out this problem with numbers. I'll tell you the reason why. There is a possibility that you will find the diameter of shaft exceeds the pitch circle diameter of the gear. There is a possibility, and that is where you have to go back. And if that would happen, so if you find this D is greater than the diameter of the pinion, clearly that is not what you want, right? You can't have a shaft diameter greater than the gear diameter. Why it would be possible? Because we are assuming that the gear is made up with a different material and shaft is made up with a different material, and the gear is keyed to the shaft. If something like that happens, the best possible way to address that concern is actually select a different material, different grade of steel, and make sure that your diameter is in a reasonable range. Now, here is a question. Reasonable means what reasonable? Typically, let's try to find out. So this is 182, right? 182. So 182 is like this such, about this much. So what would be the shaft size that you would allow? The shaft should not be greater than the dedendum of the gear. Everyone understood this? That's going to interfere. It shouldn't even be close to the dedendum radius. So I would say that this can go all the way up to maybe 75. So it should be somewhere less than 75 millimeter. And the only reason for that is because please understand, you're going to cut the teeth. You're going to cut the teeth. Then afterwards, for the shaft to go inside the gear, you are going to bore a hole. You will drill the hole on the jig boring machine. You'll bore the hole. And basically, you don't want that hole to weaken the gear itself. Are you with me so far? So how would this shaft? Okay, here is some little bit discussion. So this is the gear. So you cut the gear. Now what you want to do is you want to mount the shaft. So for that, what you will do is you will have the center line of the gear, and then you will bore a hole. Basically, first you will drill, then you'll use a jig boring machine and bore. You don't want this bore to interfere anywhere to the dedendum circle. This is going to be your dedendum circle. So because if this hole, and I think you can visualize, if this becomes bigger, the material here reduces, which means the strength of the gear reduces. So as a designer, that you want to keep these different aspects in mind. So what can be done? Sometimes what you do is, in certain rare cases, you actually construct the gear from the shaft itself. That usually happens in the case of worm gears, because worm is like a power screw and you have the shaft. So basically, once you cut the worm, the remaining part is turned into a shaft. But if your shaft size becomes too big, rather than weakening the gear by drilling the hole and boring the hole, what you do is you basically turn the shaft and you have a solid gear piece integrated with shaft. What are the disadvantages? If there are some issues, you will have to replace the gear and the shaft. But from strength point of view, sometimes this is the choice that you have to follow. Everyone understood this? One thing I want you to understand, that you will have to follow the exact same process for the shaft design of gear. Everyone understood this? Same process. But what would change? Only one thing would change. No, the diameter will be different. Yeah, no, everything else would be same. Only thing is the value of torque is going to be different for the gear. What it means is the gear shaft and the pinion shaft, they don't have to be the same. Usually they will not be the same. Gear shaft and the pinion shaft would be of different diameters. Everyone understood this? Okay, that's it for today. I'm gonna stop here and I will see you in next class.